plane string problems. Okay, so the first one is the plane stress. Those one are typically is what we call the 2D problems. Okay, two-dimensional problems. So under certain spatial situations, we might able to help ourselves to not to directly deal with the three-dimensional. We can reduce the dimension into 2D, and that can save us a lot of time in calculation, in formulation. Okay, the plane stress problem is this. The practical application of the plane stress is to apply to, say, if you have any material or any problem, that basically you have the third dimensions. Here you see, I draw it in this way. If you have the third dimensions, let me call it third dimensions. The third dimension is much less compared to the other two dimensions. Let me call this is z directions, okay? Then x dimensions and y dimensions. Okay, example of such a symbol is the thin film. Okay, and thin films will be a good model and can be approximated by plane stress. And metal sheet, metallic sheet. Okay. Sometimes people have the metal sheet, then they punch into an existing mold and form the things. Okay, and I think that pretty much is. And in particular for this case, this one being used quite a bit in the finite element software. They do have a finite element model. They using two-dimensional the model to represent three-dimensional things. Okay. Anyhow, and here the much smaller, that means the 10 times smaller. At least order of magnitude smaller. That's the definition of this symbol here. Okay, so under these situations, if assuming the z direction is in this case, then that means the stress associated with the z plane, tau dz, tau xz, and tau yz basically are all equal to 0. Okay, so under that situations, if we have the stress component, allow me to exchange the symbols 1, 2, 3 to x, y, z. Okay. So for example, tau 1, 1, 1, 2, 1, 3, and 2, 2, 2, 3, and 3, 3. And this is symmetric stress element. Okay. So that means this element, this element, this element, tau 2, 1, and 3, 1, 3, 2. So those one are 0, considered, can be approximated as 0 in such a particular material model. Okay. So that leaving only we need to consider is the two elements. And in the traditional undergrad mechanics material, in describing two-dimensional space, we always intrinsically we assume that is a plane stress. So again, in here at UNF, we talk about, is discussed in ES331. All the two-dimensional stress problems, stress strain problems are with the plane stress. Okay, but there we didn't define it because it's not necessary. But here we first time we define this one. And let me define the problem first, and then I will go further to simplify Hooke's law. Then the plane strain the plane strain is in a similar way. For the element equal to epsilon 1, 1, 2, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3, and 2, 1, 3, 1, 3, 2. Okay. Usually we have the symmetric, the 6 elements, okay? And particular model, if the material model would be like this. For example, if say we consider the cross section like this, okay, this is cross section. The cross section of certain material model. If that model, let me take this is the x direction, y direction, or that's a 1 direction, 2 direction, and z directions is in here, okay. If that model is such that in this dimensions, in the z dimensions, it has, let me use the cut. For such a model, the example could be the water dam. Okay, usually they have the features is these, the dimensions. The z dimension is much, much larger than x dimensions and y dimensions. Okay. So under these particular situations, the other possible is this. If we have the cross-sectional, and then if this is a long bar, okay. In a similar way, the dimension in this direction is much larger than the dimension in the cross-section. For example, long bar like this. So under those situations, then we know that the strain, we know the definition of the strain is deformation by original length, because the length dimension in z direction is huge. So usually this one pretty much approximately equal to 0. Okay, so in general, the definition of the plane strain is such that, for example, let me pick the z dimension or 3 dimension. Then in this way, the 3, 3 equal to 1, 3 equal to 2, 3 equal to 0, approximately equal to 0. Okay, so that means this term, this term, this term is out. Okay, so that's the definition of the plane stress and plane strain. And from here, how do we simplify Hooke's law for plane stress, plane strain? Maybe in math we can have a new section.